What's up? How's it going? Y'all will be asked to do a case study, and you can reach the case studies from the website under case study. And there's three options you get to choose from. One is heat transfer, and you can click into each one of these. Thermodynamics and molecular dynamics. So we'll review this quickly, each one, and I'll talk to you about the experimental methods as well under data collection, because you'll each be doing some experiments as part of your case study. The intent is that you would be able to do this analytically or numerically, or both, and then compare that with your experimental result. So the first one is heat transfer. And you're going to get two rods, and I'll give these to you. So one is copper and one is steel. And you're going to measure the differences in how the temperature changes with respect to position and time, or if you stick a thermocouple at a given position. And you put an end in a candle or a lighter flame. How does that temperature change with time? And so you're going to do an experimental solution, analytical, and two numerical solutions. So the analytical solution is this. So you're going to program this. And you can see the temperature at a given position on the rod at a given time is related to this function, which has the heat flux in it, which you don't necessarily know, but you're going to estimate. And this is the complementary error function. And so you have a constant heat flux solution for a boundary condition, as well as a constant surface temperature. And for that constant surface temperature, TS, for instance, it's a constant value. You can calculate or estimate the heat flux given that surface temperature and a temperature at a given node. And so I've got different tasks here for you and example code, and then you're going to compare the different methods, and so plot them simultaneously. So you can compare analytical and numerical results. And then you're also going to look at solving the heat equation using ANSYS Workbench. So use ANSYS Workbench to obtain a plot of the temperature in the rod for one of the two above boundary conditions. So you're going to pick constant temperature endpoint or a constant heat flux, and do that analytically as well as numerically, and compare that with what you get at ANSYS with the ANSYS Workbench. For the rod, a simple geometry, and then you're going to measure a temperature experimentally, and here's an example result, and you're going to compare all three of those. And here is the rubric, and there's also a rubric on the Learning Suite that will be more up to date, but this is an example rubric in terms of doing the experimental as well as the code development of numerical, analytical, and having an ANSYS plot or a representation as well as the experimental data. Then you're going to write that up. And so there's the heat transfer one, and then the molecular or the thermodynamics is you're going to measure the change in temperature once you vent gases from a Mr. Clean or a duster. I have another one here. It's a duster can where it uses, I think it's dichloroethane, DCE, I believe. And there's liquid inside the can, and when you vent it, the liquid boils, and gives you more air, quote unquote, air to clean your computer, but it's actually difluoroethane or dichloroethane. I should know the difference. Yeah. Difluoroethane, I'm sorry. Difluoroethane says right on the can. So DFE, difluoroethane, not dichloroethane. But you will vent this and measure the temperature of the gas and of the liquid. And then you compare those experimental temperatures to your numerical result. And I've given you some example code in terms of venting the gases from the can. And there's a simpler model where you just have one phase, which is the gas. And then you have a more complex one where you have two phases, a liquid and a gas. And there are some derivatives there to help you in determining temperatures as a function of time for the gas and the liquid. So you'll program all that in, complete an estimate from that numerical calculation for what the temperatures are, and then you'll compare those to an experimental scenario. And you'll be given a ESP32 and some thermocouples to measure that. And I've completed some safety calculations. For instance, if you empty the whole can into your small room, are you above the safe limit for that chemical concentration? And also do an Aspen simulation of the same scenario. And I have some helpful things here, hopefully helpful in completing that Aspen Plus simulation or Aspen HYSIS. Then you're going to write it up, document your experience. And there's an example, a rubric. And then for molecular dynamics, you're going to modify this code right here. It's basically a swelling of pellet beads. So let's see if I can play this. So you have these beads that absorb water, and they grow in size, and then they push up the height, and then it shrinks. This is just increasing in size and then decreasing, and this is the effective volume. So you're going to recreate this, but instead of 2D, you're going to do it in 3D. And you're going to do a similar kind of thing with an experiment where you have some beads. I'll give you some of these water beads, and you'll put them in a graduated cylinder and 3D print a plunger. So here's my plunger. It's hollow at the end, and then seal off at this end, but there's also a little teeny hole right there. You can see it, hopefully, that once you plunge it in the cylinder, it allows for water to escape into the cavity, and you can measure as the beads expand what the volume is. So you're going to do that experiment and compare it to a molecular dynamics like code. It's not exactly molecular dynamics, but it's more like particle dynamics estimator. So that's that one. And then you'll document those efforts. And then here is the rubric. So let me show you. So this molecular dynamics one, you don't necessarily have to have any temperature measurements, but the other two you do. And so let's see if I can show you on the screen here what you'll have. So you'll have an ESP32 There's an ESP32. And I've got right here under data collection, there's some helpful hints on how to collect the data with the ESP32. So you'll be given a thermocouple. It's a wire with different metals that when you put them together, they can sense temperature differences. And then you'll connect up the yellow wire to the positive terminal on this. This is the max, this piece right here. That's the max 6675 thermocouple amplifier. Because this voltage signal from the wires contacting is so small, you have to amplify it. And this is that amplifier, so you can connect the yellow to the positive, red to the negative. That's for type K thermocouples. And then I've got these wiring instructions for where the wires go in your ESP32. So there's the ESP32, and we'll loan these guys out. And it's flashing right now, meaning it's running. It's actually collecting the temperature as I'm talking to you. And so this is just plugged in with USB. Once you upload the code, you can just plug it into a like a charging power cord. Like, do I have one here? Yeah, like this. You can just plug it in, and it will record the data or output it, and you can connect with Bluetooth with these instructions. Right here using PuTTY. You can use the serial monitor in Arduino, and I'll show you that, or you can use this PuTTY to get the Bluetooth data to your Windows application, or you can use a Google phone as well. And there's some troubleshooting steps. So yeah, you'll use this to measure the temperature inside of your venting can, or to measure the temperature on your rods, copper or steel. So let me just show you my Arduino that I have running here. So I've got some links here, but here's an example code to be able to collect the temperature. It's pretty simple as far as putting this into an Arduino, and you'll have to import some packages for this to work, but it's this random nerd tutorial that's linked can help you get all set up. And once you have that, you can come to Arduino and just put it in and upload it. Yeah, you push the upload button, it'll upload it to this ESP32 device. And then one option, like I say, is to use the tools and the serial monitor. Let's see, where is it? Yeah, so you can use the plotter, or it's plotting right now the temperature. So if I put my fingers on there, it heats up. It's gone up to 32, 35. And if I blow on it, it'll cool down. And this green one is the time. So I don't have to plot that. So that's an option, or you can use the serial monitor. And there's your data right there. So you can actually just output it to a file as well inside the code. That's pretty straightforward to do. Yeah, so there's lots of ways to get the data off of here. One way is to stop it running and then just highlight and copy. But yeah, you can save this too, I think. Anyway, there's lots of ways to get your data off of your ESP32 for your temperatures. Yeah, God lives and loves us.